Hello and welcome to the second video tutorial of classical mechanics on statics. This is a very common problem in statics, a beam which is supported at 2 points, point A and point B. The distance from support A to the line of action of force F is 2/3 times L. So if the whole beam has the length L, the distance from F to support B has to be 1/3 times L. The given quantities are force F and distance L, and we need to calculate the support reactions. Now, what are support reactions actually? Support reactions are internal forces, like the internal force acting on the glass of water from the first video tutorial. So, support reactions are internal forces that act between the supports and our system, the beam. In mechanics, there are usually 3 different kinds of supports. The first support is called pin. The pin is able to support 2 reactions, a horizontal and a vertical force. Because if I apply a horizontal external force on the pin stays still and is not moving. This is because the pin will develop a horizontal internal force to counter the force that I applied. And if an external vertical force acts on the pin again is not moving downwards, it's staying still, because the pin will develop an internal vertical force to react to the external vertical force. But this is a hinge, okay? And what happens if a torque, a moment, is acting on the hinge? Well, the beam will rotate. This is because the hinge is not able to support an internal torque to react to the external torque. So the pin has 2 reactions, and these are 2 forces, a horizontal and a vertical force, and no moments. The second support is called roller. The roller is able to support only 1 reaction, and this is a force. And this force has to be at right angles to the ground. Yeah? In that case, it's a vertical one. The roller is not able to support a horizontal force, because if an external horizontal force acts on the roller, it will move sideways. It will not stay still, okay? So there is no internal horizontal force. And the roller, again, is not able to support a moment because this also is a hinge. And the third support is called fixed end. There is no hinge at fixed end, and this means that the fixed end is able to support 3 reactions. 1 vertical force, 1 horizontal force, and also a moment, a torque. Okay, so let's go back to the beam. How do we calculate such support reactions? As I mentioned above, support reactions are internal forces. And as you remember from the first video tutorial, we just can see internal forces if we separate the system. So if we want to see our support reactions, we first have to separate the supports from the beam, okay? This is always the first step we have to do. Separate the system from the supports and draw in all forces that act on the system. Okay. We then get 3 parts, the beam on one hand and the 2 supports on the other hand. So in the beam we have 2 forces acting at point A, Fa y and Fa x, let's say, according to our coordinate system, x and y. There are 2 forces because there was the pin, which is able to support 2 reactions. As you should already know, the direction of Fay and Fax does not matter. They just have to be drawn at opposite direction on the other part of the cut. This is the nature of internal forces. This is always the same. At point A, we just have 1 force, Fb, because there was the roller, which is only able to support 1 reaction. Again, the direction of the force Fb does not matter. It would also be possible to draw Fb in a way that it is pointing downwards. You just have to draw it in the opposite direction on the other part of the cut. So, this is our system, the beam, with all forces acting on it. Of course, we have the other parts of the cut, support A and support B, with exactly the opposite support reactions acting on them. But we don't care about that supports. We're just interested in our system. I mean, of course, these forces, Fax, Fay, and Fb, yeah, they are exactly the same forces like Fay, Fax, and Fb on our beam, on the system. These are exactly the same forces. So, usually I would say you can choose with which part of the card you want to start calculating. But in that case, we would not be able to calculate Fay or Fax if we just look at support A. And we would not be able to calculate Fb if we just look at the support B. Okay? Because they're just unknown quantities. We can't calculate these forces. So we just forget about these supports and have a look at our system, the beam. We see 4 forces. Okay? And one force is known, and this is force F. Fay, Fax, and Fb are unknown quantities. And exactly these forces are the support reactions. We want to calculate Fay, Fax, and Fb. So the next step is we need to put our system in equilibrium. There are 3 equations of mechanical equilibrium. The first one is the sum of all forces in x direction has to be 0. The second one is the sum of all forces in y direction has to be 0. And the third one is the sum of all torques concerning any point has to be 0. So let's start with the first equation. The sum of all forces in x direction has to be 0. If a force now is pointing at positive y direction of our coordinate system, it has a positive sign in front. So we have plus Fax, because it's pointing at positive x direction, is equal to 0. We have no other force in our system that is acting in x direction. The second equation is the sum of all forces in y direction has to be 0. So we have Fay positive, because Fay is pointing at positive y direction, minus F, because force F is pointing against the direction of the positive y-axis, okay? And plus Fb, because Fb again is pointing at positive y direction. And the third equation is the sum of all moments concerning any point has to be 0. Theoretically, this could be every single point on our system. But indeed, there are just a few points that we could choose. This is point A, point B, and the point where F is acting. Okay? Because for these 3 points, we know the dimensions, we know the distances. Of course, the sum of all moments concerning this point, for example, has to be 0. But we can't take this point for our equation because we do not know the distance between any line of action of our forces to that specific point. Now, which point should we take? We should always choose a point where as many unknown forces are acting as possible. Because if a force is acting on that point, this force does not cause a moment concerning this point. Okay? So this force does not appear in our equation. In that case, a good choice would be point A, for example. Because at A there are 2 unknown quantities acting, Fay and Fax, and these 2 unknowns will not appear in our equation. Also point B would be a good point, because we will lose Fb, which also is an unknown force. This point would not be a good choice, because if we take this point for our moment equation, we will lose the only known force, and this is not very helpful. So let's take point A for our third equation. The sum of all moments concerning point A has to be 0. So we have Fb times L, because L is the distance from the line of action of force B to point A. And L also is at right angles to the line of action of force Fb. This moment has a positive sign in front because it's rotating in the same direction like the positive direction of the rotation of the coordinate system, counterclockwise. We also have the moment minus f times 2/3 times L. 2/3 times L is the distance from the line of action of force F to point A, yeah? Which is at right angles to the line of action of force F. This torque has a minus in front because it's rotating clockwise and against the positive direction of rotation of a coordinate system. Yeah? Actually, I want to say that the sign of the moments does not matter. The only thing you have to be careful about is that if two moments rotate the same direction, they need to have the same sign in front, and if two moments rotate the opposite direction, they need to have a different sign in front. Okay, this is the only thing. You could also say minus fb times L and plus f times 2/3 times L is equal to 0. This is exactly the same equation. The important thing is these two moments are rotating at opposite directions, so they need a different sign in front. Okay, so as I mentioned above, the forces Fay and Fax do not have a moment concerning A because their line of actions are pointing at point A. You can say the distance at right angles to that forces are 0, so according to the definition of the torque has to be 0. So now we got 3 equations for 3 unknown quantities. Now the last step is we just have to solve this system of equations. Just for remembering, we can solve a system of equations if we have equal or more equations than unknown quantities. Yeah? In that case, we have 3 unknown quantities, Fax, Fay, and Fb for 3 equations. So we can solve this system of equations. From the first equation, we directly get Fax is equal to 0. If we have a look at the second equation, we see that there are 2 unknowns, Fay and Fb. So we can't solve this equation at this time. But if we have a look at our third equation, this one, the sum of all moments concerning point A is equal to 0, we see that there's just one unknown quantity, and this is Fp. So from this equation we directly get Fb is equal to F times 2/3. Okay? So we can just put this term on the other side of the equation and divide by L, and then we get this value for our force Fb. If we now just insert Fb in the second equation, we get Fay, and this is exactly F times 1/3. Now the problem is solved. See you next time.